So open vSwitch. Okay, so let's start with a question. No scar for this question, sorry. Who knows what open vSwitch is? Raise your hand. That's good. I was a bit afraid that people here would just come and try to learn something about open vSwitch, and then I will start with something really hard and difficult. So this doesn't work. It does. So new features. Let's just first try to make sure that we know what we mean by new features. So the current version of Open vSwitch is 2.4, was released in August. It's like half a year ago. And actually this version came after 1 year gap. So the previous version 2.3 was a year before that. And obviously during that time, a lot of development happened and a lot of new features appeared. So this talk will be mostly about 2.4, but also about 2.5, which is going to be released soon, hopefully even this month, maybe in March, if everything goes well. And actually, I will be talking about few features that will go even beyond that, to 6 or maybe even later, depending on how fast the developers are. I will be mostly okay. As you probably know, Open vSwitch has several data paths. Data paths can be kernel data path or user space data path. I will try to cover both, but focus a bit more on the kernel data path. So just for reference, the current kernel version is 4.4, released just a few weeks ago. The upcoming is 4.5. And I will cover also these kernels during this talk. DPDK, I don't remember what's the current DPDK version. It's not so much important now. So from the high level view, the new features can be divided into like 5 groups. First, improvement in the OpenFlow, because the OpenFlow standard specifies quite a lot of things, and not all of those are implemented in Open vSwitch, so new things are being implemented constantly. And the committee that is responsible for the OpenFlow standards is just adding things even more quickly, so there's always something to add. Next, quite a big topic is tunneling. There was a lot of new stuff with tunneling that happened in the past year. The third topic is connection tracking. That's actually quite important stuff. We will talk more about that. And related topic is network address translation. And the last point I want to cover, although just briefly, is Oven. Really new, shiny stuff. So let's start with the OpenFlow. One of the nice things that is new in Open vSwitch 2.4 is bundling. Now we can add, delete, and modify flows using one command, and if we specify the bundle option, it creates OpenFlow bundle, which means that all of those flow modifications have to happen atomically and together. So if any one of those would to fail, all of those are not committed and not executed. Also, if this is done, then the changes appear atomically at once to all packets, to all operations on the flow tables, and so on. So no more situations like when you are deleting flows and adding flows and packets keep coming in between, and you are in a bit awkward situation that packets can match flow that you didn't intend to. So this solves that. To make this easier to use, the add flow and add flows syntax was enhanced. Now you can actually specify a keyword in front of the flow rule to specify whether you are deleting flow or modifying flow or adding a new flow. So yeah, since now all flows are deleted by add flow command. But yeah, of course the del flow and other things that still works. There are many more features or many more new stuff with OpenFlow. I don't want to cover everything. Mostly such as small things that are usable in particular scenarios. So just one more, and it's Conjunctive Match, which allows kind of matrix match, like kind of match this packet only if the source address is in this particular list of IP address and destination address is in this another set of IP address at the same time. Right? Up to now, this actually required to have like n times m flows set up, which is quite inefficient. So if you matched 4 source addresses and 4 destination addresses, you would have to have 16 flows installed. Sucks. So Conjunctive Match solves this. Its usage is a bit weird, but then what with OpenFlow is not weird? So can it actually point? I don't know. I think it does. Yeah. So what you do is establish a rule with conjunction ID that, if matched, would do something. Like in this case, it outputs the packet to the first vport. And then you set up rules with a special conjunction action, which first argument is the ID, and second actually specifies which part of this set this matches. So this would mean that, and the actual action or the conjunction it will only match if all of those parts are satisfied. So, yep. Let's move to channeling. That's more interesting. So there were a few infrastructure enhancements, like generic enhancements. The one that's quite a new or quite interesting, although invisible to most users, is conversion to lightweight tunnels inside kernel. So up to now, when you created, say, a VXLAN interface in OVS, it was some kind of weird internal interface. If you run ifconfig or IPA, you didn't see that tunnel interface. It was internal to OVS. The not so nice thing about this was that there was quite a lot of code duplication in the kernel, because the VXLAN kernel interface and VXLAN code in the kernel module, VXLAN code in Open vSwitch kernel module was really many of code was duplicated, and that caused problems with implementing new features and so on. So this was finally unified. Now, when you create VXLAN interface in OVS, you see an actual kernel VXLAN interface, and the same for other tunnels. It's still backwards compatible. You don't have to worry about that. Open vSwitch is used exactly the same way as before. So this went to kernel 4.3 and will be backported to various distribution kernels. We also got support for user space channeling over VXLAN, Jiri, and Jiri. That's in Open vSwitch 2.4. Its usage is quite non-intuitive. The setup of the DPDK tunneling is a bit hard, but can be done and works. So I spoke about GNIV, GNIV. I think the correct pronunciation is GNIV. It stands for generic, networking something. I didn't write it down, so I didn't remember. So GNV protocol is a protocol that's kind of specific to OVS currently. It's not much used outside of OVS. It's actually designed by the OVS authors. And it's really similar to VXLAN, but it can carry metadata. So you can add quite a lot of metadata to headers, which is really useful for some use cases, and we get to that later. So support for GNV tunneling was added to OVS 2.4, but only the upcoming 2.5 release adds support for actually matching on the metadata and setting it. And it's done using TLV, type length value, and it's really generic. So using the new command add TLV map, you can add actual or specify actual TLV attributes, and then later set them using the set field action. Yeah, that sets this value or adds this value to the GNV header using this TLV. So this class, this type of this length, and similar for other. So this rule actually adds two TLVs to GNV metadata area, and the constructed encapsulated packet is sent to vport 2. On ingress, we can match on metadata. Again, as usual, this is mask, and this is the value, so it can be masked, making this more useful. Another new thing is tunneling over IPv6. Up to now, OVS did not support tunneling over IPv6 at all, so this is new stuff. Again, will be in upcoming 2.4. You also need the kernel 4.4 for that, so that means that's this the current kernel, the newest released one. Currently, tunneling over IPv6 is supported for VXLAN and GNV, and its usage is really similar to tunneling over IPv4. It was actually one of the design goals. So let's say that we create a VXLAN port, and we specify that we will supply the source and destination address later using the actual open flow rules. So this will be the OVS command to create the port. This is the same, no change here. It's exactly the same as with IPv4. And then we can create open flow rules that will actually do the tunneling. And again, it's really similar to IPv4, except we have this IPv6 keyword or IPv6 string. So if we want to set the source address for tunneling, we store that to ton IPv6 source variable or whatever. The same for destination. So it's really simple. Again, on ingress, we can match on these things as well. So we match on IPv6 source address and can do the right thing, direct the packet as appropriate. Or the second option, again, the same as with IPv4. This is even simpler actually. You may not specify the destination source destination address using OpenFlow rules. You can just make it fixed by creating the interface. So you just specify IPv6 address. You're done. Nothing more. So this is really simple. There will also be support for IPv6 tunneling using user space data path, for example, the PDK. This is going to be in either 2.5 or 2.6 OVS release. It's not clear yet. I don't know whether Tadeu has new info. No. 2.6 probably is more likely. Well, tunneling stuff. I probably have to mention MPLS. It's not so new. It went to kernel 3.19, but that was actually after the last DEF CONF. So Yeah, so it's kind of new feature in the last year. Anyway, speaking about kernel data path only, because that was supported even before for user space data path. And the example of usage is here. So there's push MPLS action, which push the MPLS header on front of the packet, specify the ether type, and then you can set fields, set the MPLS label and other stuff, and on ingress match that, pop the MPLS header, and so on. So yeah, again, nothing complex here. But there's a lot of new stuff happening. That's not yet merged, that is currently worked on. One of these things is NSH. NSH is kind of weird stuff. It's kind of similar to Jiri in some kind or in some way. It's kind of similar to MPLS in other way. So the intention of NSH is to actually carry metadata between various switches over wire, actually, or even inside host in various format. And the way this is done is quite often this is encapsulated in stuff like vXLAN GPE or Jiri or other stuff in L3 mode, which means that the tunnel does not, or inside the tunnel, inside the packet, in the inner headers, there's no Ethernet header. So you take just IP packet without the Ethernet header and encapsulate that inside vXLAN GPE or Jiri or whatever, and then possibly adding NSH header between vXLAN GPE and the actual payload. This means that now we're dealing with L3 tunnels, no Ethernet header, no L2 headers, but OVS is strictly Ethernet based. So it expects that every packet has Ethernet header in front of it. And it's really hardwired, hard-coded in various places in OVS. So this is a limitation that obviously has to be lifted. Actually, there are patches available for that. They have some issues, so they are going to be resent, and they are not yet merged. So it's likely they will go to OVS 2.6 or maybe even later. It really depends on how well this goes. When this is done, it will be possible to really direct or to add more interfaces of more kinds to OVS bridge. Like right now, you can add tab interface to OVS bridge. With these patches, you will be able to also add tune or TAN interface to OVS bridge, or vXLAN GPE and stuff like that. So there will be new push, most likely. Nothing is really certain at this point. As I said, these patches are not yet merged. So there are likely to be two new actions, push ETH header and pop ETH header action, which will add or remove the Ethernet header. The first version of the patches actually pushed empty Ethernet header, meaning the source and destination MAC address was all nulls or zeros. And then you would use set field action to actually populate these fields. Also to ease switching between L3 and L2 ports added to the single bridge, it's likely there will be some kind of implicit push and pop actions if you don't specify otherwise, which will take care of this transparently. So NSH, I already talked about that. People really want that. Honestly, I don't really understand why, but people really do want that. So this is something that will be added, well, most certainly. vXLAN GPE. There are patches that add vXLAN GPE to the kernel already, not yet merged, currently in the process of being reviewed and being merged. So the target is probably kernel 4.6, maybe later. Again, you never know when you're submitting upstream. the earliest Open vSwitch version this can go in is 2.6 because we need L3 support for this actually. VXLAN GPE can operate in two modes, L2 or L3. Really, this is something that needs to be chosen before or while creating the interface. So either the Ethernet header is isolated or not. This was done, this actually used lightweight tunneling infrastructure in kernel. We would not be able to implement it otherwise. So the effort of the conversion really pays off now. So this is how this will probably look like, but maybe again will be maybe different. So this is the syntax. You see, the only difference is that you specify a different type. And NSH will likely be implemented as two new actions, push NSH and pop NSH, which will again push and pop NSH header. More actions will be needed to actually support setting the payload of NSH and matching on it. This is not yet clear how this will look like. There are no patches that do that yet. Again, something to be implemented. It's quite likely that first there will be some limited support of NSH and will be extended in some later version of OVS. This will be combined with those push ETH and pop ETH actions to support all those combinations of NSH and Ethernet headers. So yeah, that's enough for tunneling. I think we had enough tunneling. So connection tracking. That's the most cool features that came with OVS 2.0 or will come with OVS 2.5. You will need kernel 4.3 at least for that, for this to work. And this really adds connection tracking to OVS, meaning you can do stateful firewalling in OVS finally. This is really important for things like OpenStack or OpenShift and Docker and stuff, because now they will be able to do stateful firewalling inside their integration bridge, and they won't have to resort to various tricks as now, like creating bridges with Linux bridges with two interfaces and using EB tables to do connection tracking. So this new code allows matching on connection state using OpenFlow rules. So you can match whether the particular connection or particular packet belongs to a connection that is established already or is new, or belongs to another connection, is so-called related. For this to work, OVS has to defragment packets on ingress and refragment them again where they go out. This is transparent. You don't have to care about that. This just happened. So the theory of the operation is that the packet can be in two states. It can be either untracked or tracked. Initially, every packet is untracked. And it becomes tracked when you execute CT action, conntrack, CT for conntrack or connection checking action on that packet. It actually, the CT action takes several parameters. One of that is stable, which caused the packet to be actually forked and to continue to the table is specified, and also continue executing rules in the same table. And at that new table, the packet becomes tracked. So from that point on, you can match on those contract fields. So untracked packet does not have the contract fields populated, so you don't know whether it's established or new or whatever. So when packet is tracked, there are two more states that are interesting, and it can be uncommitted and committed. When it's committed, basically the state becomes new to conntrack, and basically save the state. You can set certain fields, and also you commit that connection, that further packets in the same connection became established. I will show the example. There are different zones. Yeah, because quite often you need to do defragmentation and connection tracking for different like VMs or different tenants. So you cannot do that in the same space. You cannot really mix traffic from different tenants. They can have the same IP address, so you could mix up their fragments. This is something that cannot happen. So you can specify actual zone. Zone is a number, and that's kind of namespace for connection tracking. So that's independent for different zones. You can also set mark or label. That's this custom number that you can store with the connection and later retrieve and match out that. So it's like metadata stored in the connection table. So this is an example. Stateful firewall, which allows new connections from port 1 to port 2, but only established connection the other way. So you cannot initiate connection from port 2. So let's look at this. It's quite complex, actually. So we have table 0. We have rules, 3 rules. They have different priorities. The highest priority rule is this one, matches on IP packets. It's quite obvious. And this is important. So when the packet is not tracked, it's untracked, then we execute this action. We execute the contract action and redirect the packet to table 1. We're operating in zone 2, but that's not so important. In table 1, the packet is tracked now. Yeah, so this, again, we have 2 rules. And we have 2 rules. One matches on new packets, and one matches on packets that belong to an already established connection. So whenever it's new, we commit the packet and output it to port 2. And if it's established, we just send it out. Yep.
Should that say output 2, or is that a new syntax?
Say?
Should that say output : 2?
It can. It's just shorter syntax. It's the same.
Is that new?
Say?
New?
I don't think so. I wanted this to be shorter, so yeah. And on the other way, actually, I think this is not complete. So you would actually have to have this more complex if you really would like for this to work. So this is really just a part of the configuration, part of the rules. Yeah, so if we got the packet from the other direction, from port 2 to port 1, again, table 0, yeah, we match this rule again, go to table 1, but now in port is 2, yeah, we go in the other way. And here, if the state is new, we drop the packet. If it's established, we send it out to port 1. So yeah, that's a simple stateful firewall. It doesn't deal with things like ICMP and stuff like that. I said it's not really complete, but yeah. Network address translation. This is another thing that will really help OpenStack and Docker, OpenShift, and all those guys. Because that will allow to do network address translation inside OVS, again, using OpenFlow rules. It's implemented, it will be in OVS 2.6, so something like, 4 months ahead or like that. And in kernel 4.6, so we will have to wait even for the kernel with this support a bit. This is implemented actually inside the contract action. So there is a new sub-action of the CT action, which do the net. So this is highly tied to contract. It's actually highly configurable. You can do SNet, DNet. You can specify IP address ranges, port ranges, and do other cool stuff. So this is example of SNet. The syntax is not yet final. It may change, so don't take this syntax for granted. So again, we have this action conntrack. We do commit. I have commit twice here. Why? Okay, so it is definitely not the final syntax. No, just one commit is enough. That's actually it's a typo. So we commit and we execute this subaction, specifying that we want the source address to be replaced by an address from this range. Yeah, so there probably will be different rules how to select the particular address from the range, or it can be random, whatever you need. Yep. So that's basically it. From the other side, yeah, from the port 2, we need to reverse the net, so translate the address back to the internal address according to net table, and that's done just by specifying NAT subaction without any parameters. Yep.
Two unrelated questions. One, does it support namespaces? So you can have multiple private addresses?
So the way this is done actually is using contract zones. So if you have multiple tenants and you want to net each other to different addresses, you use different zone in the CT action. Yeah, so that's it. It's not real namespaces like kernel namespaces, but this is what you really want. That's contract zones.
And the second question is, it's done before the routing?
There's no routing. This is switching. This is switch. So you specify flows. You insert net action somewhere in the flows, and that's it. You don't do any routing. That's just switching.
Before the routing. The limit plus routing.
If you configure, so the question is whether it happens before routing. So it really depends on how you configure it. If you configure the Open vSwitch in the way that you have an internal port that goes somewhere and is routed, yeah, of course, it happens before it goes out that port. It's really up to you. It's OpenFlow. You can program it however you like. An example of DNet, of course. It's really similar. There's nothing interesting there. You match on the particular IP address and translate it to another one. And on the way back, you just specify net, and that's it. Happens magically. Only Florian understands that, and maybe Hannes. Yep. So the net will be really interesting thing in 2.6. With the upcoming 2.5, there's another really new thing that's called Open. Open Virtual Network, and that's resides inside OVS project, but it's kind of high level or higher than OVS. It's an interface between so-called cloud management systems like OpenStack and Open vSwitch, and it does it takes the logical view of the network as those cloud management systems have, yeah, like OpenStack view of the network, of the logical network, and translates this to actual OpenFlow rules on actual nodes. Yeah, so basically this is some kind of generic code that will do the translation from the virtual networks to the low-level OpenFlow rules and flow configuration. So that will make life easier, I guess, for a lot of projects. And the theory of operation is that there is a cloud management system plugin that actually communicates with so-called northbound database. And through North daemon, this communicates with southbound database, which communicates with open controls on individual nodes. Yeah, and during this chain, the rules are translated back and forth. So everything is nice and happy. I don't really have time to go through that in details. Interesting thing about this, or thing worth note, is that through each packet that travels the logical network has metadata appended through the whole, throughout its whole life and its whole traversal of the network. So that means that to use all the features that are needed, we need a protocol, Tunonic protocol that can carry those metadata between hosts. So this is why Owen is based on gnev. You can use VXLAN too, but you lose some features, and there are some not so trivial things that or limitations, like you can have only one endpoint for each VXLAN and so on. So let's not go into details. There's a bunch of other features that I won't cover. You can read them, like DPDK vhost support in OVS 2.4 that actually speeds up handing of the packets from OVS to VMs. You no longer have to go through kernel. You can directly to QEMU. Since 2.5, even with multi-queue for vHostNet. There is more QoS support, more Linux kernel QDisk supported, and you can set up. There's Mac flooding mitigation implemented, multicast snooping, MLD, bash command line completion, which is very nice, finally in 2.4, and so on. So I'm almost out of time. We have like 2 minutes for questions, I think. Yeah.
In the filter, there's this concept of related connections. How does it translate to OpenVSwitch?
Can you repeat the question, please?
So the question was that NetFilter has the concept of related connections, and how can this be expressed in conntrack in OVS. So it's quite easy. You see those flags here, to track, new, established, so there's flag called REL. So we just use that, and that's it. Good question. Sorry. Another question? Yeah.
For IPv6 tunnel endpoints, it appeared here that kernel 4.4 is required. Is that the case?
Yep. So it's kernel 4.4. It has support. That's for kernel data path, obviously. Yes.
So for user data path, does that work in kernel 4.3?
For user space data path, obviously you don't care about the kernel support, but it will be in kernel 2 in OVS 2.6 only, probably. Probably. Maybe it will make 2.5, but it's not likely. Do you want this?
Thank you. Slightly tangentially, but do you know what happened to conntrack D? Is this still around? Is it dead? Do people care about it? Or because it was a great thing once upon a time.
Conntrack D. I have no idea. That's probably a question more to NetFilter developers. You want to answer?
So I don't really understand the question. So conntrack D is basically for two things. So one is for replication to multiple firewalls for redundancy. And the other one is to do experimental protocol helpers in user space, but I don't think anyone ever uses that except the developers. So it's just about replication, and it should just work, actually, because as far as I've seen the patches, and I didn't see anything that would interfere with conntrack D and the way it works. So
I'm actually not sure whether something like that could be implementing using OBS controller. Maybe, not sure. Probably not now. We would need to have some kind of notifications about new connections, which I don't think is there yet. I mean, there's probably no protocol to pass this information from OVS to OpenFlow controller right now. Not sure.
Okay, so thank you, Jiri, for your presentation.